In this video, we'll work through examples of calculations for a first-order reaction using the linear form of the integrated rate law. And we'll start by deriving the equation for T1 half. Whenever we're deriving any equation for T1 half, we initially set two relationships. The first one is A equals A naught over 2. In other words, A equals 1/2 of the original concentration, and the other relationship is T equals T1 half. So we'll substitute those into the linear form of the rate law, the first order rate law, and we get ln of A naught over 2 equals minus KT1 half plus ln A naught. The next step is to subtract ln A naught from each side, so we have ln A naught over 2, and all of this is part of that natural log, minus ln A naught equals minus KT1 half. Remembering the rules of logs, we'll just write this up above. ln x minus ln y equals the natural log of the quantity x over y. And we'll apply that to our ln's with the A naughts. When we do that, we end up with ln of A naught over 2 divided by A naught. So I'm just going to write that in the denominator, equals minus KT1 half. The A naughts will cancel, and we're left with ln of 1 over 2 equals minus KT1 half. The next rule of logs that we'll apply is the ln of x equals the negative ln of 1 over x. What we have is the ln of 1/2. So if we take the negative of that, we can flip that to be negative ln 2 equals negative KT1 half. Canceling the negatives, basically multiplying each side by negative 1. And we have ln 2 equals KT1 half. Remember, we're solving for T1 half. So divide both sides by k, and we get T1 half equals ln 2 over k. And this is familiar to you. You've seen this equation before. What's worth mentioning is that the ln 2 is exact. So you will ignore that for your sig figs. And when you use this equation for any first order reaction, the sig figs are going to come from the sig figs in the rate constant k. As we'll see later, nuclear decay reactions are always first order. So whenever you are going between T1 half and k for a nuclear decay equation, a nuclear decay problem, this is the form of the half-life that you will use because it is first order. Now we'll calculate a half-life. So let's start by writing our equation. T1 half equals ln 2 over k. All we need is the rate constant. So even though we're given the original molarity, that isn't part of the first order equation for T1 half, and so we just don't use it. So T1 half equals ln 2 over k. I'm going to write the k by itself, so that way I can be very clear about the units for k. So any numerator units and denominator units will be fully separated. K is in the denominator, so I start writing it there. 2.0 times 10 to the negative 3 inverse seconds. So I'm going to flip the seconds to the top. And there's nothing here that will cancel. half-life is a unit of time. That means that however the units work out, you have to be left with units of time. Keeping track of the sig figs, as we said a little bit ago, ln2 is exact, and in this example, k has 2 sig figs, so this t1/2 will be rounded to 2 sig figs. So we take the natural log of 2 divided by 2.0 times 10 to the minus 3 gives us 346.6. This needs to be rounded to 2 sig figs, so I'll just put this in scientific notation. 3.5 times 10 to the 2 seconds. Or, in this case, you can write it in decimal notation as 350 seconds. In our next example, we're going to use the linear form of the first order rate law. I'll go ahead and write that down first, and then we'll define our terms. ln A equals minus kt plus ln A naught. The information that we're given, calculate the concentration of A. So that's what we're trying to find out. After some molarity of A, which is going to be our original molarity, even though it's not defined as A naught, the problem tells us that that's what we're starting with, so we know that's the initial concentration. Reacts for 12 minutes. That's our time, and K is K. We always want to rearrange the equation first to solve for the variable of interest. In this case, the ln A is already isolated. So we'll plug in the values, we'll solve for ln A, and then we'll take the antilog to get A. I think that way is easier than trying to combine everything into an exponent for the antilog. You just have to make sure that when you're all done with the calculation, you realize that what you calculated was ln A, and there's one more step. So ln A equals negative K, so negative 8.03 times 10 to the negative 3 inverse minutes, so I write that in the denominator, times T, which is 12 minutes, 12.0. The units of time work out, so there's no other conversion we have to do there, plus ln of A naught, which is 0.1060. We don't need to include the molarity units, the concentration units, because you can't take the natural log of a unit. Taking a look at sig figs, we have 3 sig figs for K, 3 sig figs for time. So when we multiply those together, we need to end up with 3 sig figs, but then we'll figure out what that means in decimal places. The sig figs for the natural log, we have 4 sig figs, which will become 4 decimal places. Doing these intermediate calculations for the first term, the KT term, we have negative 8.03 times 10 to the negative 3 times 12 minutes gives us negative 0.0964. That's 3 sig figs, plus natural log of 0.1060. So we need 4 decimal places for that second term. That gives us a negative 2.2443. Because we have an addition subtraction now, we have to report the fewest number of decimal places. The first term has 4 decimal places. That's what our 3 sig figs results in. And our second term also has 4 decimal places. Because each value has 4 decimal places, when we do the calculation, we will want to end up with 4 decimal places. Doing the math, we have negative 0.0964 plus a negative 2.2443, and to 4 decimal places, that gives us a negative 2.3407. Be really careful about negative signs when you're dealing with these types of problems. It's easy to lose one along the way. Our last step is to take the antilog of each side. So e to the ln A equals e to the negative 2.3407. When you take the antilog of a log, you just end up with that quantity. A will equal the antilog e to the negative 2.3407. The rules of sig figs go in reverse. So we have 4 decimal places here, and when we take the antilog, we need to end up with 4 sig figs. So doing the math, we end up with 0.09626. And the units are molar. In this next example, we'll apply a similar strategy. We'll write our linear form of the integrated rate law. ln A equals minus kt plus ln A naught. We'll define our terms so we see what we're trying to calculate. The question reads, how many seconds, that's a time, that's what we're trying to calculate, does it take for the concentration of A to decrease from 0.0500, that's our A naught, that's where we're starting, to decrease from 0.0500 to 0.0100. So the second concentration is A, and then K is K. We're trying to solve for time. So in this example, we will rearrange the equation. So we want to isolate time. The first step will be to subtract ln A naught from each side. So we have ln A minus ln A naught equals minus kt. We need to get time by itself. So we'll divide both sides by k. K will cancel over here, and we're left with t equals ln A minus ln A naught divided by negative k. Now, if you want to further condense this into a ratio within that natural log term, that's fine, or you can leave it like this. We have everything we need to plug in. We have ln A, which is 0.0100 minus ln A naught, 0.0500, and that quantity divided by negative k. I'm going to write the k as its own term. It's in the denominator. We have 3.99 times 10 to the negative 4 in the denominator. Inverse seconds, so the seconds flip to the top. Taking a look at the sig fig rules for our first term, the subtraction of the ln's, both of the terms are the same. They each have 3 sig figs, which will turn into 3 decimal places after we do the subtraction. And so that result will be to 3 decimal places. Let's go ahead and do that first. So we have the natural log of 0.01 minus the natural log of 0.05. That gives us negative 1.609. I just realized that I forgot my negative sign over there with K. Be really careful about that. So our 3 decimal places ends up to be 4 sig figs. And then we'll apply K. So we have seconds on the top, negative 3.99 times 10 to the negative 4. The value of K has 3 sig figs. So our final result is going to have 3 sig figs. So we have negative 1.609 divided by negative 3.99 times 10 to the negative 4, and that gives us 4,034. 3 sig figs will be 4.03 times 10 to the 3, and our units are seconds. Our last example, we start with ln A equals minus kt plus ln A naught. Our terms are, we have the concentration of A, we have time, 3 minutes. We want to calculate the initial molarity, which will be A naught when the experiment started, and then we have K. So for this example, we need to rearrange the equation to solve for A naught. To isolate that term, we just need to add kt to each side. ln A plus kt equals ln A naught. And like the earlier example, we'll solve for ln A naught and then take the antilog. So plugging the numbers in, we have ln A naught equals ln A, which is 0.0021, plus K, 5.52 times 10 to the negative 2 inverse minutes, so the minutes will go to the denominator, times time, which is 3.00 minutes. So time will cancel. We don't have to do anything else there. Taking a look at the sig figs, our natural log term has 2 sig figs. So after we take the log, that will be 2 decimal places. And our kt term has 3 sig figs and 3 sig figs. So we'll end up with 3 sig figs, and we'll see what that means in terms of decimal places. ln A naught equals natural log of 0.0021 negative 6.17. That's our 2 decimal places, plus 5.52 10 to the negative 2 times 3, 0.166. Because the next step is addition, we need to see what these look like in terms of decimal places. We have 2 decimal places for the first term, 3 for the second term. So when we add these together, we need to round to 2 decimal places. And when we do that math, we end up with negative 6.00. We're not done because we have to take the antilog. Let me just rewrite this so we can see all the work right next to each other. So we take the antilog of the first term and the antilog of the second term. The rules of sig figs go backwards for antilogs as compared to logs, so our 2 decimal places are going to end up as 2 sig figs. So when we do the math, when we take the antilog of negative 6, we end up with 2.5 times 10 to the negative 3, and the units will be molarity.